I want to stay at a fairly high level, conceptual level. You probably, how many of you have used Amazon EC2? Can I get a show of hands? So just under half or something thereabouts. That's about what I expected. Feel free to shout out any questions anytime. I'd be happy to take them. So cloud computing and databases. So when you read about, or the definition of cloud computing is about infinite or virtually infinite resources available on demand, pay per use, delivered across the internet. What I think is often overlooked is that from a technical point of view, sort of technically what excites me the most is that it is a fully automatable infrastructure. So when I make an API call to Amazon EC2, obviously the virtual machine that's provisioned is provisioned fully automatically. But not only that, I can build automation on top of this and have a completely automated system and operate a completely automated deployment on top of it. So I can automate as much as I have the stomach to do so. And that really changes the game in the way, at least for me, I operate production or test deployments. So from a database point of view, I think what this means to me in operating is that infinite compute resources means I can have as many database machines as I want or need at any point in time. So it becomes a tool. When another database box can help me, I just go and get it and don't think about it, and it basically doesn't cost me anything. Obviously, everything costs something, but the fee is nominal and often disappears compared to the time I'm spending. And the automatable part saves me work, saves me time therefore, and also makes it more reliable because things are more reproducible. So I want to put some color behind all of these statements and just walk you a little bit through the way we do things and how we see this playing out. So just to start with the automation part. This is sort of on one slide, 4 of the big use cases that you'll hear everywhere about cloud computing, right? When I have this traffic spike and I'm in the headlines, then I can scale up on demand and launch more machines. If that's not somewhat automated, then you're probably not going to manage to get those servers online. Just below that, the pay for average, not peak, and I'll show a customer example of that. Every day, almost all internet services have the diurnal cycles of users coming and going. And so you can, if it's automated, you can launch servers in the morning, or have the system launch servers in the morning when the load increases, and then shut them down again in the evening. And in the end, you're paying for roughly average utilization and not peak utilization, or really probably 2 times peak if you had to really build it out yourself. For test and dev, and that's something, especially in the database area, where if you want to do experiments or you wonder how much time is the schema change going to take, right? How much time is this, whatever transformation I'm trying to do, going to take on my production database when the system is down? Well, you launch another server in order to try it out ahead of time, and it costs whatever, $20 or less in terms of compute resources. But if launching this extra server, or if launching a clone of your entire production deployment to try something out meant you had to spend 20 hours installing all of the servers, configuring all of everything, loading the software up, well, then really you didn't gain anything, right? In fact, you could launch these machines where the API call didn't actually help you that much. So having the automation where the servers, it's not about just launching the server and it sort of being there at the boot prompt saying, hey, I'm here now, what do you want me to do? It's really in production, getting it to do what you want it to do. So it's there loaded with the software, with the data, etc. That's what you want. That's where you get the big difference. Scaling batch apps, batch workers in the background working off of job queues, adding and removing servers as the queue gets longer, etc. So the typical use case, and this is not particularly database focused, is scaling up and down application servers. This is kind of a standard deployment that we provide out of the box to our customers. They can configure and change to their will. But basically it starts with 2 app servers that have standard open source software, Apache, HA proxy for load balancing, hitting generally 2 app servers, probably doesn't see Java, Rails, PHP, etc. And then the MySQL master-slave replicated backend. And what customers expect is that you can set alerts on the load of the app servers. As the load goes up, the system, the RightScale backend that acts as a daemon, does the monitoring and the alerting. Instead of sending out a page for the alert, can automatically launch additional app servers. And here's where the automation kicks in. Right? It's not just about launching the machines, it's about configuring them, setting them up so they talk to the database, the right database, have the credentials for that, and wiring them into the load balancing rotation. And so if you go to the dashboard, you see on the user interface, here's the overall deployment with a row for each server, and you can set all of this up and manipulate it. And if you look at the monitoring, this is from a demo deployment that we run. At the top is the HTTP request over time. That's about a 2-hour period. And at the bottom is the CPU load on one of the fixed app servers. Green is idle, everything else is busy. And so when we see about a third in, the idle time reduces as the load goes up in the graph above. New servers are launched, and eventually they kick in, and then suddenly when this app server becomes more idle again because additional app servers launched and took some of the load off. And further back, the load goes back down, app servers become more idle, another rule kicks in, and the extra app servers are turned on. And so here's now this is sort of one of the basic things that you can do in the cloud. And I think it's, on the one side, it's very attractive, right? It's really cool to have these servers launch. Oh, look, this morning at 4 a.m. I wasn't even awake. Additional app servers launched because the East Coast woke up and added load. What we find is that this is not necessarily, this is what everybody wants when they come in, and they think this is going to be the great benefit, but it's really, for some customers, it actually works, and they have a need for that. But the other benefits more around flexibility of operating and around testing that are actually more typical, and I think of higher value. StarCut is a customer of ours. They produce mobile websites and host them on EC2. And for them, they have pretty high-profile sites, like here, there was a site for the Olympics. And they also have a lot of smaller customers. So they have a whole setup where they have one cluster for all of the small customers. So everybody who starts with no load, right? They're just experimenting, trying things out. And then as their clients grow, the sites grow in popularity, they start spinning them out and taking them out of the shared cluster and build their own private deployment just for that particular site or that particular client. And that's where, again, we're in the cloud, and when you have the automation, it really becomes easy because you have the server templates all ready to go, and spinning up another one is really just pressing a few buttons, changing some configs, and it comes up. So here's one. So that was for the Olympics, and you can see how. So this is actually a pretty short time span where it is really at a high load. So that's nice in the cloud. You have this infrastructure you have to get rid of afterwards, what to do. You see some of the spikes of some of the major events. And what's interesting also is on the left-hand side, this is where they did the tests before the Olympics started in order to make sure that they could ramp up and that everything would work. So at that point, they ended up spinning up a lot of servers that then go away again, and they didn't have to pay for it. Another example here is really a good example of the daily scaling. This is one of their sites for stock exchange. And you see the daily peak in activity, and actually there's two peaks at the opening and closing of the market. That's a good one where the reactive, that's an example where the auto-scaling doesn't really work that well because the spike is so vertical at the opening of the market that unless the server is already ahead of time on schedule, it's almost impossible to react based on sort of the loading in a single watching efficient servers. So that's a little bit the background, and maybe I should have thrown in another example. We really use the flexibility for test and dev tremendously, and that's where we ourselves get the biggest benefit from. So RightScale runs within the cloud itself as well. And being able to add additional servers in order to test something out is really where a lot of benefit comes from, or enabling the developer to spin up a whole staging environment to test the new release out for a couple of days, make it go away after that. That's really where we get a lot of the benefits. Good, so I wanted to talk up down one level and talk a little bit about the standard configurations that we use and how all of that goes together. So just a little bit of background here. This is pretty much the Amazon EC2 storage architecture. Other clouds differ slightly, and I'll talk a little bit about that. So you'll see the different providers really targeting slightly different configurations. So it's not going to be uniform as far as I can tell. So you get EC2 instances with anywhere from half a core to 8 cores, 1.7 gigs of memory to 16 gigs of memory, and 1 to 4 local drives. So it gives you anything from a pretty wimpy machine to actually a pretty big machine. You can run some serious database code. Then what's important is as a second level of the storage architecture is EBS, the Elastic Block Store. That's basically a storage array in the sky, and I'll talk some more about that because it's a critical piece in running databases in Amazon EC2. And then as a back end is Amazon S3, the simple storage service, which is not a file system, it's a click and get interface, and it is used for persistent backups and redundant backups. So this store everything in S3 is stored redundantly across multiple availability zones, think data centers. So for persistent storage and backups, that's what this works. So Elastic Block Store is really what I wish I would have had in my previous job in terms of SAN storage to a large degree. You can create a volume anywhere from 1 gig to 1 terabyte in size, and it's available within a couple of minutes, oftentimes in a few seconds. You can attach this block device to one instance at a time, which means you can detach it and reattach it to another instance. I actually recommend not to ever do this, but I'm not getting into that. It has to be in the same availability zone, so you can't attach a block device across data centers with another instance. It's one at a time, so you cannot. So in terms of the sharing, I think the two big limitations currently in EC2 infrastructure are that you cannot mount or share a block device across multiple instances to run something like a cluster file system. And also the other one is there's no multicast at the network. So you can't, and you have to, you're limited to UDP and TCP. So some of the sort of block level, Ethernet level protocols you can't. The cost is 10 cents per gigabyte per month, which I think is pretty low. And then there's this 10 cents per million I/O operations cost. And at first, that drove me a little bit nuts because now I can understand the 10 cents per gigabyte. I can map this out in my mind, right? But can you map out what the cost is going to be about these million I/O ops? Do you know how many million I/Os your database does in a month? I'm sure you don't. unless you really go and dig around and look into it. So my experience has been that I think if you run 100 IOPS per second sustained for the month, then it starts to show up somewhere around, what is that, $90 or somewhere. It starts to get into the $100 range, which for me starts to mean it's become significant. In other words, it starts becoming comparable to the instance cost. Right? Otherwise, it's kind of down in the noise. So it tends to be down in the noise for most uses that I see. The other important aspects of EBS is that you can do a snapshot backup of a volume to S3, and we use that very heavily, and you can create a new snapshot, a new volume from a snapshot. Just to talk about the snapshots, they're point-in-time snapshots, so that's the nice part. They're written to S3 in the background, so the benefit here is that you get back channel to your disk array, so that that data doesn't need to travel through your machine, your instance, as you're pushing it to S3, which was the old model. So it's sort of a back channel that pushes out in the background. It runs at about 20 megabytes per second, which is not super fast. So the first time if you fill a volume with 50 gigs of data and you say take a snapshot, it's going to take a while, meaning probably a couple of hours before it completes. The good news is that after that, snapshots are incremental. So only the changed disk blocks get pushed to S3 when you do subsequent snapshots. So the more frequent you do the snapshots, right, the less data you will have changed, the faster they will complete. So at some level, it's almost beneficial to make it as frequent as you can stand, and as opposed to letting them age forever. And the restore is instantaneous, which isn't possible. Right? You can't get all of this data back from S3 onto a disk instantaneously up to a terabyte in size. So what's happening is that it is on demand. There's a background process that fills your volume with the S3 data pulled from the snapshot. And if the instance requests a block that has not yet been restored, then that read blocks. The block is fetched from S3 when it arrives to be dissatisfied. So that means that startup, essentially the disk volume can go pretty slow while everything is being restored. So just on the incremental, what happens is that the first time we do a snapshot, all of the blocks are written to S3. There's a table of contents in S3 that ties them all together. The second snapshot, 2 blocks may have changed, so those need to be written to S3, and the table of contents can point to the old blocks from the old snapshot, and it continues like that. So at the end of the day, it's pretty hard to tell what is the S3 usage, how much data is contained in one snapshot, or if I deleted this snapshot, how much would I save in terms of storage cost. So that's one of the downsides, that it's hard to get a handle on that, and unfortunately Amazon doesn't provide any good information on that, which they could since they do have the information. Right, so the lesson here is using the snapshots heavily and doing them frequently. So just a couple of things. These are somewhat low-level details, but I think it's important to keep them in mind. You're probably familiar with this, with any SAN storage structure, that if you're doing snapshot backups, you need to freeze the file system. XFS is nice because it has a freeze command, so you can really freeze the file system itself and ensure everything is flushed. To our great consternation, there's a bug in the 2618 kernel that is pretty much a standard kernel on EC2 that can cause hung file systems. And that has bitten us a couple of times, has bitten a bunch of our customers a number of times. It's not fun when your master database just freezes, and any process that touches the disk volume just hangs and is unkillable. So we actually currently run without doing the XFS freeze, and we haven't seen any negative consequences, but and we're waiting on there's a fix out that is in your kernel, requires rebuilding a bunch of things, so we're in the process of getting there. It's unfortunately not an easy bug to reproduce. At least we can't reproduce it reliably, other than running a production system on it and hitting it after 2 weeks. So that one has been nasty.
Just a question. So Amazon's, when they snap on EBS, they don't guarantee freezing costs at their position.
Okay, so the question is whether...
Extra safety, what?
Right, is this extra safety? What does Amazon guarantee regarding the snapshots, etc.? So EBS exports a block device, and the block device is network attached, so it sits in a redundant manner on external servers. When you snapshot that, it's a point-in-time snapshot. There's a point in the request sequence where the snapshot is taken and the disk blocks are backed up. So what you don't know is, from the instance's point of view, from the database executing transactions against the file system writing things to the block device, at what point this occurs. So it can be right in the middle of a whole bunch of changes, which then require file system recovery and NOTB recovery. So if you want to get a clean snapshot where you don't have things in flight and grab it at an arbitrary point in time, you should freeze. So lock all tables and freeze. Initiate the snapshot through the API command, which takes a couple of seconds, and then unfreeze. So the effect is that your database will be for a couple of seconds in order to execute this. So again, you need to have some timeouts around it in case the API call doesn't come back, so your database is not locked for too long. So it's the usual mess, pardon the word, that you need to write to wrap around that. The other part is that I think most people, when they first look at the snapshots and the volumes and the ability, start with a model which is, well, so the instance can be changed. Well, that means really my database is my EBS volume. Right? So I basically put my database onto this EBS volume, and I'll do the snapshots. Those are my backups. And if I want to roll back, then I can restore an old snapshot. And if the instance, something happens to the instance, so I want to upgrade from a large server to an extra large server because the load has gone up, then I'll just shut down the instance or unmount the volume and then fire up a new instance and mount the volume onto the new instance. And in principle, this works, but it's not a good way to think. There's a couple of reasons. One is that, and sort of the alternate way, is that you always go through a snapshot. So don't even think of the volume persisting. The volume is just extra storage on your server, and you always make snapshots. And if you want to move this data to a new server, you pick a snapshot, or you create a snapshot if you don't have one recent enough, and you create a fresh volume from that snapshot. And that gives you a couple of things. One is, if something happens during the mount that is not good, then you will not destroy the volume with all of the data. Obviously, in a perfect world, this never happens, but if you've ever tried to mount the disk volume using the wrong file system, or forgetting that there was LVM partitions on there and tried to mount it as a whole drive, or any of those combinations, you experience interesting kernel crashes and data corruption. And if this was the volume with all the data, then goodbye. Whereas if it's created from a snapshot, you can start over. You just go back to the snapshot, create a fresh volume, and off you go again. Also, volumes can't be mounted across availability zones. So if you wanted to launch a server in a different availability zone, maybe there's some data center failure, some fire or something that causes a massive outage in the data center, then again, going through a snapshot gives you that flexibility. So basically the the setups that we end up with is that each database, each slave, if you have multiple slaves, continuous has its own EBS volume, and we take snapshots, backups from the master on an infrequent basis, and then as frequently as we can stand, typically every 10 minutes on the slave. And the reason here is if the slave is frozen for a few seconds, big deal, no impact on production, but it's nice to have backups of the master, so we use InnoDB basically exclusively unless someone knows what exactly they're doing. But it's still nice to have backups of the master just in case something happened with the replication. Yes, question?
He says how long let's say the condition can last. The master will make these backup.
Yes. So the question is how long is it frozen? And that's an interesting one because there's no guarantee around the API call. Right? The question really is, at the end, your instance or RightScale on behalf of your instance making an API call to Amazon EC2 to say snapshot this volume for me now, please. And when the API call returns, the snapshot has been initiated. And that's when you can unfreeze the file system and keep going. So in a situation where, and we've seen that this takes typically less than a second, and sometimes it's 1 or 2 seconds. We haven't really seen this go on forever. But we have a timeout wrapped around those calls. So if in your app it is asked if once a day it hangs for more than 5 seconds, you have a 5-second timeout. You just give up on the API call, unfreeze, and then try again a minute later or whatever your policy you want to set up as policy for that. So kind of looking back at what did I do prior to using EC2 and EBS. And I was chief architect at Citrix Online, ran online service 24/7, also responsible for the data center operations. We had nice Oracle HA setup with a master and a slave. And kind of the first 2 bullet items here were the typical fight between me and my DBA, where something fails in the master, and that means we failed over to the slave. Great, we're still up and running. And now we have this little tug of war here of me telling him, okay, get it fixed and bring it back up. And especially if the failure wasn't hardware caused but was software caused, he'd look at me and say, but Thorsten, I don't know really what broke. I need to reproduce it. If I just bring up the master again, or the database box again, and bring it up as a slave, then it's going to happen again next week. You don't want that either, do you? And so eventually we had enough money, so we had a 3rd machine, and it became a 4th machine, and there always was 1 to 2 machines in order to do what we wanted to do. Another one is testing a schema change or migrating to new hardware, where then you start looking at where do you have space in the rack, do you have enough SAN ports, are we running out of ports on the SAN, we need to upgrade that before we can add 2 machines while we're going through the upgrade, and we need twice as many machines as we need before or after, etc. And really here in the cloud now, a lot of this goes away, right? Because leaving the old failed master limping along, sitting around for a few days, may cost you, $20 or $100 even. And that cost, if it's a service that is producing revenue, is just totally, at least in my book, totally insignificant. If it gives us the ability to go back in and to poke around at the thing to see whether we can understand what went wrong and fix it. But in the meantime, we've already launched the new servers in order to be, again, in a replicated setup. Right? So it's always go and get the next server. To give you a little bit of an example of how this works is this is kind of the typical upgrade from a smaller machine to a larger machine. So clone the server configuration in the UI, change to make it the new one a large or a larger machine, launch it. As a slave, it comes up automatically, synchronizes with the master, starts replicating, promote it to master, and launch a fresh slave. So these are all fully automated steps that you can really click and go through, and there's actually a demo in a webinar where we do it live within 10 minutes or so. And we've done this on live deployments on production, and that works very well. And really having that flexibility is tremendous, at least in my book. So now the cloud principle is always go and get the next one. And that's where good sysadmins are really awful, right? Almost every good sysadmin I know, there's a problem. The first reaction is, oh, no problem, I think it's throwing, and let me check, I'll fix it real quick. And no, don't do this. Don't do it. Something is broken, let it sit there, launch the next one. You have it automated, you should have that all scripted and it's all ready to go. Once the new one has taken over, then you go back and figure out what went wrong. The other dimension that I think is important is that this whole automation, right, and this is where for me it all comes together, is the cloud enabling this whole automation, and the automation then really has impact on how we do the ops, how we do the work. Many small databases, I think, are a lot easier to handle. There's lots of people talking about that in the community, provided you have the automation that goes with it. Right? If it's just a lot of databases out there, then it's a nightmare to manage. But if most of the operations, all of the operations are automated, then it is really possible to manage that and to keep the databases smaller and to have more